Thanks for the presentation. And now let's come to the next one. It's from Animesh Trivedi and his collaborators in RDMA Research Zurich. The title of the paper is a case for RDMA clouds, turning supercomputer networking into commodity as well.
Thank you. So I'm Animesh, and I'll be presenting our work, which titles "A Case for RDMA in Clouds." And this was a joint work between Bernard Mutzler and Patrick Swady at IBM Research Lab Zurich.
You don't know if the microphone's working?
It's green.
Hello? Yeah, there.
Okay. All right. Is it better? So, we are living in a data-centric world. Everything around us, laptop, computers, smartphones, sensor nodes, they are continuously generating data. And there's growing tendency to actually push and store all this data into the clouds. And to analyze, and more importantly, to make money out of this data, we also have a large number of distributed data-intensive applications running in those clouds. So the performance of those applications depends heavily how fast they can get access to this data. In other words, it depends upon the networking performance. And with the increasing demand for the more real-time analytics on the data, it puts tremendous pressure on the networking stack of the cloud to support high bandwidth, ultra-low latency, and at the same time, it has to be energy efficient. So let's have a look at the networking hardware, what's been going on there. So bandwidth is not a problem. Network capacity has been improving by 10x every 5 to 7 years. We have seen with megabit Ethernet and gigabit Ethernet. 10 gigabit Ethernet is now commodity, and we are a couple of years away from having 40 and 100 gig Ethernet. However, what has changed is the single CPU speed improvements. So in the past, because of the Moore's law, it was able to catch up with the increasing link speed, but not anymore. So the gap between the link speed and the CPU speed, CPU's speed is widening, and it will be broader in the future. But we do have many of those cores that we can utilize. But how to fully utilize many core systems is still a challenging problem, and let alone the parallelization of the networking stack. So the other direction to handle this problem would be to make a single CPU more efficient in handling the networking traffic. And this is the primary focus of our work. So during the talk, we'll have a look what commodity clouds and supercomputers have in common. We'll compare their networking stack side by side. We'll have a little bit detailed look at one particular supercomputing network technology called RDMA. We'll see why RDMA is potentially a good fit for the cloud, but there are some challenges. And we'll move on to see why having RDMA in software makes sense. We'll talk briefly about our implementation, which is called SOC-IWAP. We'll give some performance number, and with some concluding thoughts, we'll finish the presentation. The commodity clouds. So everyone knows they handle lots of data. They have petabytes worth of data in them. They have thousands of cores. They are made out-of-shelf machines. They use commodity networking, Ethernet to connect and shuffle around the data. So what about supercomputers? They also have petabytes worth of data. They also have thousands of cores. But to handle the performance and other things, they have customized hardware and tailored networking stack to actually support the performance requirement of the applications running in supercomputer. But the one thing that they do have in common that they both require efficient networking to shuffle around the data and facilitate fast inter-process communication on the between multiple processes running on a different node. So what do they have as a networking stack? So in the clouds, you run normal applications which use socket-based TCP/IP interface, and supercomputers have their own proprietary implementation for the networks. And these are the things which we are interested in evaluating in terms of the merit what they offer. So high bandwidth, yes, they both can offer high bandwidth. User experience, well, socket-based interfaces have 3 decades of user experience with them. We have been using them since 70s and 80s. Supercomputers are kind of restricted technology. NICs, well, they use commodity NICs. That's kind of things we are interested in. Supercomputers have their own customized expensive NICs. But socket-based interfaces cannot support those ultra-low latencies that supercomputer can. They don't have a rich API. They only just support send and receive. And last, they are not CPU efficient. To actually drive those things and support all these characteristics, it's a heavy CPU bound. So what? Sorry. So how do they achieve these things? So yeah, we know that we have a customized hardware stack, but at the same time, they also have developed these communication semantics, software principles, and API associated with the specialized hardware, such as RDMA. And in this work, what we are interested in to actually complement the benefit of socket-based approach to from the good part of the supercomputer-based networking approach. So what is RDMA? So you can think it as an extension of a classical DMA concept, but for the remote nodes. So in a normal DMA, the CPU tells the drive or DMA engine that I want to read and write memory at this region. But instead of giving the address of a local memory, it gives the address of a remote node, which is connected through some, let's say, interconnect. So what NIC does in this case, it transfers the buffer data from the application buffer from this side to the NIC, to the interconnect NIC, and back to the application buffer. And it's as simple as that. And it's based on the user level networking concept, so it separates the data from the control path. So before you actually initiate the transfer, OS and application have to set up some, let's say, some few things in the beginning for the permissions and other. And once those things are done, data is moved freely from the application buffer to the NIC and back and so forth. And they also have associated asynchronous, semantically rich network API. And we know that this design has served supercomputers so far very well. They've been able to support all the requirements from the supercomputer, and that's what we need. But there are some challenges to actually apply RDMA in clouds. Well, they do require special networking hardware that doesn't go very well with the commodity nature of the clouds. And these NICs are expensive and they have a limited life cycle. And they do the transport protocol offload, which is kind of a messy in a mature commodity operating systems as Linux. They don't support transport offloading natively. So you have to have special patches and things in order to support it. And since everything is handled in hardware, the resource management for the network-related things is kind of rigid. There is no scope to do on-demand, flexible resource allocation, which is essentially what cloud does. And to be frank, it's not simple. It's a very complex thing, setting up the RDMA, and it's a complete different thinking. It's a different part, and if things are offloaded in hardware, it makes really hard to understand what has been going on, and it hinders kind of end-user experience and expertise in developing the application. So, with the RDMA, there's a protocol called IWAP, which stands for Internet Wide Area RDMA Protocol. This specification enables having RDMA on top of the IP-based networks, which goes hand in hand with what clouds uses. So they use TCP and SCTP as a transport, and we can use on top of normal Ethernet. So that's good. Let's see how that stands up against the normal socket-based interface. So with the sockets, you have high bandwidth, but not low latency, not CPU efficiency, not rich APIs. Applications are involved in terms of the data transfer, but they do use the commodity NICs. So IWAP can do all these things, but at the same time, it still requires special NIC to do things. It's not that simple. But since it uses TCP IP and you can run it on top of Ethernet, it opens doors for the more software-based implementation. So technically, in a software-based implementation with some modest support from the OS, it can have high bandwidth, potentially low latency, better CPU efficiency. It can support the rich API. Application can be excluded in terms from the data path, and we can use with the commodity NICs. And this is our specific implementation of this argument. We have implemented the IWAP protocol in software. It handles RDMA traffic on the commodity NICs. It is developed as a loadable kernel module. It runs on top of unmodified TCP/IP stack in Linux. It uses in-kernel TCP/IP sockets, and it integrates seamlessly with the industry standard of OFED RDMA.